Hello again, and picking up where we left off, the optic flow field is what we want to talk about next. So if you have, at this point, a fairly good understanding of the optic array, then we're ready to go into this. If you're still confused about the optic array, I might recommend that you go back and study a little bit more. I think that you need to have a good sense of what this idea is, right? Again, it's light reflected from visible surfaces in the environment converging to a point of observation. And what I also want to make sure that you understand is that this, in this case, a hemisphere, I'd previously tried to draw it as a sphere or circle, but this is a hemisphere. It's an imaginary hemisphere. That is, we're adding that there for the sake of convenience, for the sake of visualization, that we can see how these reflected light rays converging to the point of observation, which would be where the bird's eye is here. As they intersect that imaginary sphere, there would be these little dots, right? At least when it's a stationary optic array. But since the bird is really flying, in this case, what we also have to imagine is that each one of those dots is going to trace out a little arc in the field of view, right? And that's what you also need to imagine here. And one way to kind of get a sense of this, even right now, if you want, I would maybe recommend pause the video and then go walk around in your place for a minute, right? And just keep your eyes fixed straight ahead. Walk through a doorway, walk past your couch or anything. And as you keep your eyes fixed straight ahead, I want you to also pay attention to how things move in your environment as you do that. Now, obviously, they're not really moving. You're the one that's moving, right? But by your act of walking forward, you're generating optic flow. And that optic flow is the fact that things are kind of streaming past you on the left and on the right, right? And that streaming past you on the left and the right is optic flow. That's what we're trying to depict here in this particular drawing. But now, instead of a person walking through their house, this is a bird flying over a plowed field. And so these little wavy lines on the bottom, those are meant to be like the furrows in a plowed farmer's field. And what we want to imagine is a sight line, a light ray, reflecting from every point, every little divot in those furrows through that sphere, and then aiming at the bird's eye. And wherever we're going to have a light ray intersecting the sphere, we're going to put a dot in that sphere. But as the bird moves forward a little bit, those dots are going to trace out these little vectors. And these are referred to as optic flow vectors. So now what we want to do is we want to try to determine, is there a pattern in the optic flow vectors, right? Previously, we talked about patterns in the optic array, primarily focused on the texture gradient. But now what we want to find is what we would call a flow gradient. And a flow gradient is a pattern in the way things move. So what do we have here? Well, we notice that there are some gradients here. The first, maybe most obvious gradient, well, perhaps not the most obvious, but we're going to start with it first. Notice that as you go from left to right, sort of, in the image itself. So these first row, and I hope you can see my mouse pointer. This first row, or really more of a longitudinal line of flow vectors, directly beneath the bird. This corresponds to the optic flow pattern that would result from the furrow just below the bird, right? And as we go from left to right, and I'm going to pick this one particular latitude here, and I'm going to go all the way from left to right as we go further up to the equator of the hemisphere, right? These arrows get shorter and shorter and shorter. the further to the right we go. And each one of these different longitudinal lines here corresponds to different plow rows or furrows as we go further and further off to the right-hand side of the image, which is to the left of the bird, right? And so what does it mean for these arrows to get shorter and shorter and shorter the further we go off to the side of the bird, further off to the bird's left? Well, the length of each arrow or flow vector corresponds to what we're going to call the optical velocity of that visible point. What is optical velocity? That is the rate at which the object moves in the bird's field of view. This is very much related to the depth cube talked about in the textbook called motion parallax. The idea is that objects that are further away move slower in your field of view. That is, they have a lower optical velocity compared to objects that are closer. The closest part of the environment for this bird is that part of the ground directly beneath the bird. And as we go further off to the side, further to the bird's left wing, we're getting farther and farther away, and therefore the optical velocities get slower and slower and slower. So that creates a flow gradient, right? An optical velocity gradient. This is exactly what you experience if you're riding in a car. Don't do this when you're driving, but while you're riding as a passenger in a car, and if you happen to be driving past a field, if you look out to the side of the car, you will notice that the stuff that's right on the side of the road appears to be zipping by real fast. If you're going 60 miles an hour on the highway, it's zipping by so fast, it's like a visual blur, right? But if there's a field, then maybe some trees or something on the other side of this field that are possibly maybe a quarter mile away, give or take, they appear to be moving by a whole lot slower, even though you're technically driving past all of that stuff at the same speed of 60 miles an hour. The apparent speed, the visual speed, gets slower and slower the further away things are. That's the flow gradient, right? And that's exactly what we're seeing here. That's what these ever shrinking flow vectors, the further away to the side we go, that's what that depicts. That's what that is representing here. So that's information now, right? The idea is that the flow gradient, in terms of that specific decrease in flow velocity to the side, corresponds to the depth layout of the environment. And it also then corresponds to things like the surface slant as well, because if the bird was flying against a hillside versus a level terrain, you'd get a different kind of flow gradient, right? So it does correspond to the three-dimensional surface layout of the terrain. And so in that case, now we're going to get some information about depth and distance and spatial scale because we have a flow gradient. So just like a texture gradient can specify surface slant, the flow gradient can specify three-dimensional surface layout, right? Distance and shape and positions of things relative to the ground plane and all of that. Now let's pick a single longitudinal line. We might notice that as we go out from that central point here on a single longitudinal line, the arrows also get longer and longer and longer, right? They're really small right up here in the center of the bird's field of view, but as we trace them out, they get longer and longer. So again, what's going on there? Why is it that we have another gradient, not just as we go off to the side, kind of latitudinally, but also longitudinally down a single line like that? We're getting a gradient in that direction. So there's two gradients, right? In two different directions, right? There's gradients across the latitudes of these flow vectors, but there's also a gradient within each longitude. Well, let's think about that. The longest flow vector is the one that represents the point on the ground plane directly beneath the bird, which is the closest point on the ground plane to the bird, right? And as we go forward a little bit, that point on the ground, a little bit further up in front of where the bird is currently at, is a little further away. And of course, as we go further and further ahead, those points in front of the bird are further and further away. So we have depth here, not just to the side, but depth also specified by the flow gradient in front of us as we are flying towards whatever we're flying towards, right? Or if you are walking, as I said, you may pause the video and walk around in your place. You can notice the flow gradient of things off to your side, but you also should notice a flow gradient in front of you. And as you walk towards a door, for example, you're going to notice that things that are further away, maybe something that you see through an open door, might have a lower optical velocity, but as you approach that doorway, you're going to see that the rate of the sides of the door start to pick up their optical velocity as they get closer to you. And it expands in your field of view as you then walk right through the doorway. So we're going to have these kind of optical velocity flow gradients in 2 dimensions, specifying depth layout all around us. But another more obvious pattern is the fact that all of these flow vectors are emanating from this one central point, right? By the way, this big arrow in front of the bird's nose here, that just is an indicator of the bird's direction of flight, right? Indicating that's flying straight ahead like that. That's not a flow vector. That's just an indication that the bird's flying. But it's flying in this direction towards this point. And if we follow that arrow out from where it's flying, we see that it points to a dot on the equator of this hemisphere, right? And all of our flow vectors seem to be radiating outward from that one central dot. Why do we only see flow vectors in this one little quadrant of the hemisphere? Well, the artist here drew it this way just so that it wouldn't be overly cluttered. We could and should imagine the flow vectors are visible on the entire hemisphere, right, to the bird's left and to the bird's right. But that would make a very messy diagram. So this is just simplifying it. And obviously, we don't have the top half of the hemisphere because this is where we might want to draw some flow vectors for clouds that are above the bird, which the bird is also going to fly under the clouds, and that's going to cause optic flow over the bird's head. But we're going to focus on what the bird sees as it maybe sees the ground as it flies over the ground. So what does this mean? This central point that all of the flow vectors are going to be radiating out and really from in all directions from there. Well, that's called, we've got a few different names for it. It's mathematically, it's called a nodal point in the flow. So it's a node. But also it's called the focus of expansion, or FOE for short. And we notice that all the flow vectors radiate out from the focal point, or focus of expansion. We call it the focus of expansion because of the idea that you're having these vectors expanding outward from that point, right? And as I described before, if you walk towards an open door, you're going to see that expansion of the door frame. And it gets bigger and bigger in your field of view as you walk right through it, right? So the focus of expansion will be inside of the door frame. If the door is closed, the focus of expansion is going to be right there on the center of the door itself, right? So what does the focus of expansion tell us? It actually tells us where the bird is heading, right? So it specifies something. It specifies a state of affairs in the world. And in particular, this particular state of affairs in the world, we're going to call heading, right? So from the perspective of the bird, we're going to suggest that the focus of expansion specifies the bird's flight heading. What is it flying toward? If the bird wanted to control its flight to land on a tree branch, what it would need to do is to be able to detect that the focus of expansion is centered on the tree branch. And that would be informative because that would really be, that's a unique one-to-one relationship that wherever the focus of expansion is, that's where the bird's current flight path will take it. And if the bird wants to land on that tree branch, it needs to control its flight to keep that focus of expansion on the tree branch. If you're walking to a door and you want to walk through an open door, then you need to keep the focus of expansion on that within the front boundaries of that door frame so that you're walking correctly through the door and you don't walk into the wall instead. Because if you're walking toward the wall, that's where the FOE is going to be, a focus of expansion. You're going to walk into the wall. That's not helpful, obviously. let's take a look at our next picture here. So we're going to try to see it from the bird's eye view, or the view from the poo, as I call it. So from the point of observation, right? So again, we're now inside the sphere. We're at the bird's point of observation, or your point of observation as you walk around inside your place. And so you're going to see these radiating flow vectors coming out from that radial expansion pattern, right? We're going to have the focus of expansion. First, what does the radial expansion pattern itself mean? Expansion here meaning that the arrows are pointing outward, indicating that everything in front of you is expanding. And so, of course, that means approach, right? As you walk towards a door, it expands in your field of view. It gets bigger in your field of view, right? And so that radial expansion pattern specifies approach. The focus of expansion specifies exactly where in the environment you're approaching. The flow vectors themselves specify movement, right? So let's think about that. So what is there meaning in the flow? And again, this is a critical part of the ecological theory, that the optic flow defined here external to the point of observation contains meaning and information. It is not ambiguous. And therefore, this information could be detected and used directly without any kind of cognitive inference that has to happen. So in the presence of optic flow, is that inherently meaningful, or is there some sort of cognitive inference that has to happen? Well, let's think about what it could mean. If something is flowing, if you experience optic flow, we know something's moving, right? If there is no optic flow, we say that there's nothing moving. But we might have ambiguity, right? We possibly need to be concerned about ambiguity. And that ambiguity comes from the question, what is doing the moving? Am I moving in a stationary environment? So if you get up again and walk around in your place, you're going to experience optic flow because you are moving relative to a stationary environment. But if you are in a seated position and you're stationary, and something moves around you, the environment moves around you, you're going to also experience optic flow. So how do we know in general, when you experience optic flow, whether it is you that's doing the moving or whether it's the environment that's doing the moving? And we might think that there's possible ambiguity here. And maybe we think, oh, well, again, because there's ambiguity, do we need to have some sort of inference to figure out when it's me and when it's not me that's doing the moving? Well, according to Gibson, the answer to that is no, we do not need inference. And here's his justification for that. Gibson's claim is that whenever global flow is present, that specifies or provides information about self-motion. And whenever local flow is present, that specifies or provides information about object or environment motion. What am I talking about here? What's global flow? Global flow is when optic flow exists in the entirety of your visual field. The entire optic array is changing and moving all at the same time. That's global flow. Global flow here meaning it's all moving, right? So Gibson's claim is that global flow only happens during self-motion, and it does not occur in any other situation. Now, can we think of an exception to that? Is that an overly broad conclusion to make? Let me say it again. Gibson's claim is that global flow only happens when self-motion happens, not when there's any other thing moving around. Well, I can think of a couple of exceptions. One possibility might be an earthquake, right? That's a weird one. But if you're in a building and the entire building starts to shake because there's an earthquake, then you're probably going to experience global flow, even though it's not necessarily you that's doing, well, you're probably doing some moving because you're being shaken by the earthquake. But in that case, though, the building is shaking all around you, right? If you go to an IMAX movie or put on a headset for virtual reality, but you're otherwise stationary, standing or seated, you can experience a global flow from the screen, either in VR or in an IMAX movie, even a regular movie, but an IMAX movie has a bigger screen, so it's a bit more compelling, right? So we have those exceptions. Or, I'm going to jump ahead real quick. You might remember the moving room experiment. I'm not going to repeat everything that we already did about the moving room experiment that I covered when we talked about the perturbation experiment in the perceptual constancy notes. But what we see is that in the moving room experiment, that's in fact an unusual situation in which our subject here, a toddler, is experiencing global flow, even though they themselves are not the thing that's moving, but it's the room moving around them. I also have on the next slide of the video embedded from YouTube of that. I already showed it to you from the constancy notes. So I'm just going to skip all of that and come back here. And so this is, again, just a depiction I don't think I showed you before, which shows the moving room surrounding our subject. And as the room moves, that away, in this case, the room is moving to the right, which is away from the subject. That causes the perception of falling backwards, and the response is to try to lean forward, and we see a depiction of somebody falling on their face there, right? So that's the idea. So it seems, is it possible that Gibson's wrong here? That global flow always means self-motion? Well, we have to pause that for a second and think about what Gibson is trying to claim here, which is from what we might consider to be an ecologically valid perspective, global flow always corresponds to self-motion. Ecologically valid meaning that when we think about the evolution of visual systems, animals did not evolve to handle perceiving virtual reality displays or movies and other kinds of projection type displays like that, right? Artificial displays. Nor did visual systems necessarily evolve to handle the unique circumstances of earthquakes, which are probably quite rare in general for most seeing animals, right? So the idea here is that in 99.9999999 whatever % cases, global flow will correspond always to self-motion. And the fact that with modern technology we can simulate that doesn't mean that the ecological point is not true, right? That in a natural viewing environment, global flow really does always correspond to self-motion. So that's what we're seeing here, is that I have a depiction of global flow on the bottom left there from the bird's eye view, person's eye view. And we see above that then a depiction of a person who's walking over ground and generating global optic flow. Local flow is then the opposite, distinct from global flow, because of the idea that now only a small portion of the visual field is exhibiting some movement, and therefore flow is localized to that one spot. And this would be an object. So in this case, somebody has thrown a ball, the ball bounces up towards the person here, and we're going to experience some optic flow just on the boundaries and surface of the ball itself, right? And so it's that local flow. It's never going to be the case, right, that self-motion would generate only local flow, right? That if you're walking through your house and you're only going to see optic flow on one thing and everything else is going to be stationary while one thing moves, that's going to be weird, and that's never going to happen. So local flow really does uniquely correspond to object motion. I'm going to come back. We're going to talk more about local flow later. I'm going to skip on past our stuff here on the moving room study. I think we have that down. What I want to talk about here, following up on that moving room study, this idea that expansion, radial expansion, also known as outflow, that specifies approach, right? It specifies that you are approaching, since this is global outflow, where I intend to suggest here, that specifies self-motion towards a surface, right? So again, when you're walking towards a door, you will experience global optic flow because it's self-motion, but because you are approaching the door, you're going to have that expansion pattern and or AKA outflow pattern in the global optic flow. On the other hand, if you are standing in front of a door and then you just start walking backwards, you're going to experience inflow, or what we might call a contraction pattern in the optic flow, where now all the optic flow vectors are going to reverse direction. And instead of radiating outward from a focus of expansion, they're all going to converge inward to what we could call a focus of contraction. And just like the focus of expansion will specify your heading direction, what you're moving toward, the focus of contraction would also specify the I don't know what the opposite of heading is, right? But it's what you're moving away from, right? And so that inflow contraction pattern specifies retreat when it's global inflow, right? So global outflow specifies self-motion approach towards the surface. Global inflow specifies self-motion retreat from a surface, right? I have some other pictures, or not pictures, videos. Here is a depiction of optic flow, just again, because it's so weird to try to visualize optic flow from all of these drawings. It's nice if we have an animation to help us see optic flow. So this is sort of like your classic Star Trek kind of a thing, right? The spaceship flying through space and the stars are flowing all around. But we're seeing optic flow here, at least an abstract representation, right? If this was, let me just hit that again. If this was a cluttered environment with objects, right? Then the objects, right? So again, if you get up and walk around, you're going to experience this kind of flow pattern that specifies approach. You get this radial expanding pattern, and you're going to end up, just one more time here, with a little bit of a depth gradient that kind of gives an impression of moving through a cloud of dots in this case because of the flow gradient that's happening off to the sides and the top and the bottom. So you get that, again, you get this impression of moving through space. I have another one that's, so here's, yeah. Here's, again, the pictures are only so about depicting optic flow. But in this case, again, we want to say that, what am I walking towards? So if a person on the left is walking towards the doorway at the end of the hallway, then you're going to see that radial expansion pattern, radiating outward, flowing outward from the center of that door marked A at the end of the hallway. But on the other hand, if we change our heading and we start aiming for that door on the left, then we're going to, see the flow radiating outward from that point. So wherever that focus of expansion is in our field of view, that's going to tell us what we're walking toward, right? And that's kind of useful information. Now here is an animation that kind of gives us this idea. I see myself moving. It's like you're taking a step forward a little bit, but if I start and I go another direction, then we see all the flow vectors. I'm going to hit it again. We're going to see all the flow vectors just going one direction or another direction. And that's providing information that tells us a lot of things about what direction we're going, right? What direction is the object, is all that flow happening, right? And the direction of all of that flow is telling us some things about where we're going. Here's another horrible static image trying to capture the concept of flow, right? But I have one more video. This one doesn't necessarily directly depict optic flow the way those, flowing dot patterns do. This one is really just a person holding a camera and taking a walk through the forest, right? So, of course, you just watch this for the sake of seeing some trees, but pay attention to the visual motions, right? Look at what's happening as we see the trees that are close to the path right in front of us. They are expanding, but as we get closer, the more they're just going to start flowing off to the sides. And look at these trees that as they pass by, they kind of appear to be moving faster because they move through the visual field quickly, while trees on the further away in the forest appear to kind of stay more or less stable, right? They move at least a lot more slowly, right? So whereas things that are close to the person walking move by quickly. So we're going to see a flow gradient as detected as the relative motions of all of the tree trunks, right? And you're going to get this expansion pattern and flow gradient that tells us about the spatial layout of all of these objects in the environment. So there's a lot of optic flow being generated here. This is a 3-hour video of a nature walk, so we don't need all this, right? But I just want to play a little bit of that to get the point across that there's optic flow, and that's what it's like. I want you to be able to visualize and understand the concept. So what we have seen is that there's a lot of meaning so far in the flow, right? Global flow is meaningful, local flow is meaningful, outflow is meaningful, inflow is meaningful. The focus of expansion, or FOE, is meaningful because that specifies your heading direction. A change or shift in the FOE from one location or visual angle in your visual field to another would specify a change in your heading direction. So we have all of this information, and I'm going to run this back a little bit here if I can, past all these videos, back to our local flow. So focusing only on global flow so far, again, let me repeat one more time what I just said. There's a lot of patterns, and the claim here is that these patterns uniquely correspond to a certain state of affairs in the world. But when I say uniquely correspond, that's just another way of saying that there's a one-to-one mapping between the visual pattern and a state of affairs in the world. Global flow uniquely corresponds to self-motion. Local flow uniquely corresponds to object motion. Outflow uniquely corresponds to approach, especially global outflow corresponds to self-motion approach. Global inflow uniquely corresponds to self-motion retreating, walking backwards away from something. The focus of expansion uniquely corresponds to your heading direction in the world. Some of the same things apply to local flow too, right? So I want to point out here in this drawing that we see the local flow because there's a ball bouncing towards our little stick figure person here. There is a little focus of expansion centered on the ball itself. And so there is a radial outflow pattern there too, right? And that specifies approach, but because this is object motion, this does not specify that the person is walking towards the ball. It specifies the ball is coming towards the person, right? And in fact, the mere fact that there's a FOE on the ball specifies that that ball is actually going to hit you, right? If that ball was thrown towards you, but it was thrown poorly, so it was going to pass off to your left, then there would not be a visible focus of expansion on the ball. All the flow vectors on the ball would be pointing in the same direction to one side or another, and that would specify whether it's going to pass to your left or to your right. If you want to catch it, if you're playing baseball and if you're a fielder and your goal is to catch the ball, that means you need to get in front of it, right? You need to get in its path so that you're in a position to intercept it. And one way to do that is to move yourself in the way of the ball. And how do you know you're in the way of the ball? Because as soon as you get in the path of the ball, you're going to place a focus of expansion on the ball. So visually, the fact that all the flow vectors shift from going sideways in one direction to now being within the boundary of the ball is enough to tell our baseball player that they are in the path of the ball and they are in position to field it, right? And that's good if that's what your goal is. If you're playing dodgeball and you want to get out of the way, you want to do the opposite, right? You want to move away. If you see a focus of expansion, you know it's coming at you, so you need to duck or jump to one side so that you can make it miss you, right? So that's information that's useful depending on your goals, right? If whether you want to catch it or get out of the way, the presence of the FOE or absence of the FOE tells you whether it's going to hit you or not hit you. So there's another pattern, right? The fact that it's expanding means the ball's coming at you. Imagine if you throw the ball. If you're the one holding the ball and you throw it away towards another person, you should see a focus of contraction on the ball, right? You're going to see that ball shrinking in your field of view as it contracts. And then it's because it's moving away from you, there should be a focus of contraction on the ball, right? So local expansion means object is approaching you, and local contraction means the object is moving away from you, right? A lot of patterns here. But there's one more pattern in optic flow that we want to talk about, and I'm going to save that for another video because it is a little bit mathematically involved. And it's called, not just looming, as I have titled it here. The looming effect is really just the fact that when something is coming at you, it kind of gets bigger in your field of view, and it looks like it's going to hit you because, of course, it is. But it's there's this other property that we might want to know about an object that's approaching you, not just whether and if it's approaching you, which we just covered, but also when is it going to hit you, if it's coming to hit you, right? So if someone throws the ball at you and you want to catch it, it's useful to know exactly when it's going to get to you, because you need to know when to get your hand up and close your hand around it and catch it, right? So you want to know what we call time to contact information. Time to contact is how much time until this thing contacts me. And the next question is there information in the local optic flow that specifies time to contact? In fact, this could also be applied to global optic flow, by the way, right? If I'm walking towards a door, I might want to know what is my time to contact until I get to the doorway. And so there's, whether it's global optic flow or local optic flow, the question is as I get closer to something, or that something gets closer to me, how much time left until that happens? That could be very useful information, but the question is there information that will tell us what that is? And that's going to be our next point, next video.